wake up at 8 o'clock on Monday morning. Let's see. Go, Hey, what do you say for coffee and class notes? There's actually a link for that. I was not like that note. Okay.
Hey, can you guys hear me? Anybody hear me?
Yes.
Oh, good. All right. Thanks for the feedback. I'll wait for people to get in here.
Every time there's a link, we have to create a class.
I gotta tell you, I tried to do a little Zoom meeting with my sisters last night, and it took us a half an hour just to make sure that we all had our audio and visual video feeds going. So I'm pleased that you guys are able to make it work faster. Oh, wait, let me turn off my clock here. I have a clock that chimes the hour very loudly, and I don't want that to interfere with the class. All right, I'm going to give people a couple of minutes to log in if they want to. While we're waiting, does anybody have any questions? Anything that you want to share? You guys going crazy yet, staying home all the time? I had a meeting this morning with the dean, and as it turns out, our dean has a daughter who's a freshman here at UT, and so he's getting information from both sides. And he said, you know, speaking as a dean, I can tell you that we're trying hard to get everything back to normal when it's going to be possible to get it back to normal. And speaking as a father of a freshman, he said that his daughter is giving him a lot of impetus to really get everything straightened out really fast, because she's hating this idea of trying to run all of her classes just off of her laptop in her bedroom. So we're all trying to pull through and get it to work. All right, guys, you ready to get started? First, let me pull out my notes here. All right, so the first thing I got to tell you is if you look, you'll see that the homework that you're currently working on, I've pushed the due date back a full week, because I realized that when I tried to meld the homework from the previous semester with our messed up schedule from this semester, that I got the weeks all kind of mixed up. So as far as I can tell, you've only got enough information as of today to get you through about the first 6 questions on the homework. So if you haven't started it, give it a start, and try to get the first few questions, at least get those set up. Okay, Enrique, I think you have your mic on. Can I cut somebody else's mic off? Okay, yeah, thanks.
Sorry, that was on accident.
Yeah, that's fine. I figured it was. Hey, so I had a good time the other night. I looked up Zoom fails, like on Twitter and Facebook and stuff, and people have done some pretty bad things when they're having a Zoom meeting, like picking up their laptop and taking it with them and setting it on the floor as they go to the bathroom, and then everybody can see them go to the bathroom. So let's all try to be mindful of when our mics are on and when our video is on. Anyway, so first 6 questions, you should be trying those. That'll tie in with what we can which you should be able to do already. And then the other questions will be more about the stuff that we'll be picking up with. Maybe we can start it today, but I suspect it won't be until Monday that we'll start it. And that's all the stuff having to do with different coordinate systems and transformations. We're going to be doing that. It's going to come up real soon. And that will involve things like doing integrals in polar coordinates instead of Cartesian coordinates. All right, so do you have comments or questions that you want to give me about at least the material that we've done so far, or those first few homework questions? All right, let's return to this use of Fubini's theorem. Oh, we have a question. Brianna.
Hi. So I had a question about number 2 on this homework that's available now.
Yes. Can you remind me what the question is?
It's like 2 cylinders in the first octant.
Oh, yes. And they want the volume of the intersection or something like that?
Yes. Yeah.
Okay.
I just am kind of confused on how to, like, I guess, set up the, like, area and then, like, I guess find the bounds for the integral.
Okay. Good question. Yeah. It's a good question. So, right. So I will show you, and we'll actually compute an integral. But I want you guys to focus on the fact that at this stage in the chapter, we're still spending a lot of time just trying to make sure that we understand why integrals give us the answers to questions like this. So let me put my document camera on, and then I'll show you what to do. Maybe this light will help. Yeah, that's a little better. All right, so yeah, there's a picture that goes with this, and I'll try to recreate it a little bit. So in the first octant, they ask you to intersect a couple of cylinders. So you should imagine there's these 2 pipes that are intersecting. There's one along that axis and another one along a perpendicular axis. And well, it's not immediately clear what this is going to look like unless you've seen a junction where some welder has brazed together a couple of intersecting cylinders like this, a couple of pipes. In practice, what happens is that you always see a seam here along the 45-degree line. It's curvy, so I'm trying to make it look like it bends a little bit, but on this portion here of the intersection, it looks just like it's a part of a cylinder, but then there's a different cylinder coming in from a different direction over here. And how do I show that this is in the first octant? Just that much there, and this much over here. So there's the place, there's sort of the outside of the intersection of these 2, and then there's the inside, which is the part they want you to get the volume of. Now, it's really hard to try to get a single integral that represents the combined volume of all the part that I've shaded in here, the entire part of the intersection that's in the first octant. It's easier if you just look at half of it. So if you look at half of it, I'm going to draw this piece back here. There's the circular arc that comes from the top from this cylinder, and then there's this let me make sure I'm drawing the right one. There's the straight edge that comes from the fact that they only want you to look over the first octant, and likewise a straight bottom. But then it goes from here, it goes back along this edge. This part of, there's a straight line segment here across the top. I guess I'm drawing this one like that. It's straight across the top, and then it curves around because of the other intersecting cylinder that's coming in. And this is the part that's a little hard. If I drop a perpendicular here, that's not a part that you would be able to see from the outside of this intersection of the 2 pipes. But inside there, you could drop a perpendicular that would come right down to the origin in the XY plane. And extending from there out to this point, that's right here in the original picture, then at this point, the intersection of the other cylinder kind of doesn't matter. I've looked here at the points, I'm showing you here only the points where this cylinder is higher than this cylinder. Wait, shoot, I got it backwards, don't I? I need the part where this cylinder is lower. Damn it. Sorry. Crap. I need the part where this cylinder is lower. Let me draw that again. Where this cylinder is lower is here, but only up to here. And down like this. There we go. Okay. Well, that's probably easier to see than this one anyway. Okay, so again, they want you to get the volume of this whole shape, but by symmetry, that's going to be double the volume of just one of these two halves. And I'm choosing, after some deliberation, I'm choosing this half over here, what looks like kind of the back half or the right half. And the reason for that is if you're intersecting the two solid cylinders, the volume that's inside both of them is the volume of the region that's under, whichever one of them is lower. The lower roof is the one that you actually see if you're standing on the floor looking up. You see whichever of the two roofs is lower. And so I think I've shown the one that's lower in the back. It's this one that's lower than in this half. And on this other half, it would be this cylinder that's the lower piece. So, are these cylinders of radius 1? I don't remember the exact problem. I hope they're the same radius. That makes the calculation a lot easier. Do you remember, was it Brianna that asked, are they both cylinders of length of radius 1?
Yeah.
Okay. So I can actually write down the equations of the cylinders. That might help. Those are the X and Y axes. Then here you see a circle in, where it intersects the YZ plane, you would have a circle of radius 1 centered at the origin of the YZ plane. And so that circle would have an equation y squared plus z squared equals 1. But the exact same equation, treated as defining a surface in three-dimensional space, it gives me exactly this cylinder. Since there's no x's mentioned in this equation, you can have any x coordinate you want, and you'll get the points that are in the cylinder because you've chosen the y and z coordinates to lie in the circle, and then you allow the x coordinate to be anything. And likewise, the other cylinder would have the equation x squared plus z squared equal to 1. So I need those pieces of information to describe what I see happening in this picture. There is, on the back, I see a quarter of a circle in the YZ plane, and that circle is again given by this equation. And that equation describes all the points that are on this, well, on the entire cylinder over here, but in particular, it describes this portion of the roof of the little wedge piece that I've illustrated in this smaller diagram. That is the roof, the highest point that you would get if you were standing anywhere on the floor of this picture. That little floor is a triangle, and for any person who's stuck inside there, if you ask them how high the figure is for them, the height of the roof is determined by this cylinder, not the other one. That's why I'm restricting just to half of the picture. So it makes my life easier to only focus on the one cylinder. But the price that I have to pay for it is that I have to be standing on that triangle. That triangle is the set of points that are closer to the y-axis than they are to the x-axis. In other words, their x-coordinate is smaller than their y-coordinate. So this one edge of the triangle is the set of points where the two coordinates are equal. Another edge of the triangle it's the set of points where the x-coordinates are as small as possible, x equals 0. And the third edge of the triangle is the set of points where the y-coordinates are equal to 1, because that's how far away you're able to go from the x-axis when you draw this cylinder. So if I've done the picture correctly now, the volume of half of the region they're asking us about, can I call that the half volume? The half volume of the, or in other words, half of the answer that they're really looking for is going to be the volume of the region that lies over this triangle and at the same time under that surface, under the surface given by this equation. So you can, if you think of, anytime that you're asking for the volume of a region that's over a subset of the plane and under the graph of a function, that volume can be calculated as an integral. It's the integral over exactly that little triangle. And you, what the function you're integrating is the function that you're graphing. In other words, it's the function that gives you the z coordinate as a function of the x and y coordinates. And it's an area integral of the type that we've been describing. You, just to recap, you would imagine chopping up this little triangle into a bunch of little parts, a bunch of little tiles, and then on top of every one of those tiles, you want to build a tower whose height is given by the height of this surface right above this spot in the xy plane. And the height of this surface is given by the z coordinate of a point that's down here on the triangle. And the z coordinate, you see from this equation, you could figure out what the z coordinate is if you knew exactly where you were standing. This z coordinate will always be, let's just solve for z here, it's the square root of 1 minus y squared. And that's the function of the two variables that I need to integrate over this triangle in the xy plane. So, you notice I haven't done any integration yet, and I certainly haven't gotten the answer, but I do want you to see how I thought about the problem to represent the answer, or half of the answer, as an integral. Does somebody want to stop me on that much? All right, if you're not going to stop me on that, then I'm going to keep going, and now I want to compute the integral. So now you can put the
Dr. Rusin?
Yes, go ahead, Kyle. Oh no, Noah. Wait, Noah, go ahead.
Could you describe what's next to the integral, the first integral? It's, your video's coming on our end very, very blurry.
Oh, okay. Yeah, it's a little blurry for me too. I don't know why that is. I've done the same thing that I've done every other day, except I added a light. Does that make it any different? All right, you're asking about this integral here?
Yes, sir.
And what part of it is it that you want me to clarify? What this is down here?
I think the TA just explained the integral so that we could see it. So, but I think someone just had a question about the like what it says in that very first integral right under the word half volume.
Right, the half volume. What I wanted you guys to see is that it's the half volume of what we're looking for. It can be described in words first as being the volume of the region that's over a portion of the xy plane and under the graph of some function. And anytime you put those words together, that kind of a volume that's over a region in the xy plane and it's under the graph of a function, that volume is calculated as an integral. You integrate over exactly that region in the xy plane, and the function that you're integrating is whatever function it was that you were graphing. Whatever function is giving you your z coordinates as a function of x and y. So that's the theory of integration coming in there. That's like the first stage of all of these problems. You need to be trying to figure out how to express the volume or whatever else it is that they're asking you to get as some kind of an integral. And when I say some kind of an integral, you always need to specify the function that's being integrated and the portion of its domain that you're integrating over. So yeah, please do either ask me or ask the TA to make sure that you can get that far. Because the rest of it now is just a bunch of algebra, and I'll show you in a second Fubini's theorem. Here's the algebra. that just says, oh, you want the z-coordinate? Well, the z-coordinate can be computed from the x and y coordinates. As it turns out, we don't have the x coordinates in here because of the way this figure looks. Everything is stretched out along the x-axis. So it's kind of an accident in our particular problem that there's no reference to x. But in general, you solve for z, and that's the function you want to integrate. Now, the rest of it is not so much theory as it's just using Fubini's theorem. And we had Fubini's theorem last time. We discussed it first for integrals over rectangles, but last time I started to show you how you could use this for integrals over non-rectangular regions too. So let me rewrite the problem here. So it's the integral over a triangle, and the function we're integrating is this. And specifically, well, okay, so it's this triangle where it's bounded in the xy plane by these 3 line segments. One of them is the x-axis, the y-axis. Oh, well, yeah, I'll try to make it look like you usually put the y-axis vertical. So there's the y-axis was part of it. That was the equation x equals 0 in there. Also, the equation x equals y showed up. And finally, the equation y equals 1. Those were the equations of the 3 lines that made the boundary of the region that was on the floor of this little figure. 1, 2, 3 equations. So, how do we use Fubini's theorem to calculate the integral of a function over a set like this? Now, I showed you a little bit last time, but I want to make, I want you guys to get used to hearing the words, at least the words that I say as I go through setting up these integrals using Fubini's theorem, because we're going to need it a lot, even for the integrals in 3 dimensions, which we're going to do today, and the integrals in other coordinate systems, which we'll probably start on Monday. So here's the way to set this up with Fubini's theorem. You know you're going to write this as a double integral, where the integrand is going to be exactly what it was in the previous description. You're going to write this as an iterated integral where you integrate with respect to one variable at a time, and Mr. Fubini didn't care which variable went in which order. So you get to pick one of the 2 orders for the integrals. You can put dx first or dy, I don't care. But surround one of them with square brackets for clarity. I mean, you don't have to, but I think that that's useful. And then give yourself a little reminder as to where the limits of integration, which variable the limits of integration are going to refer to. Since you've got y's on the outside here, you'll want to put y equals for those limits of integration, and likewise x equals for those limits of integration. Now, we've got to figure out what goes in these 4 spots, and we do that by working from the outside in. So you need to wander over to this set that you're trying to integrate over, and you need to start talking to all the points that are in the set and asking them about their x and y coordinates. We're going to first do it for the y coordinates. So for that, I'm going to wander over the entire set, asking each one of the points what its y coordinate is. And I need to write down the least and the greatest values of the y coordinate that are found anywhere in the set. Of course, if you're looking for small and large values of the y coordinate, the way to do that is to go in a certain direction. Which way do you go inside of the figure to get the least possible y coordinate of a point? North, south, east, or west? Which way gives you the lowest y coordinate? Anybody? I'll wait. Which way do you go? South. Yeah, you go south. So going south gives you your minimum y coordinate. And if you go north, you'll get your largest y coordinate. So in this figure, to get my smallest y coordinate, what I will do will be to go as far to the south as I can, and I can see that there's clearly just one point that will give me my smallest y coordinate. What I need to do into this spot is to write the y coordinate of that point. Now, I guess you guys can probably see in the picture what it is, but let me show you how, in general, you're going to have to calculate these. This point, which is at the bottom edge of my figure, the south edge of my figure, yes, I know it's going to give me the smallest y coordinate, but how am I going to get that minimum y coordinate? it will come from writing down the two things that I know about this point. If you're in two-dimensional space, every point has two coordinates, and to figure out those two coordinates, you need two pieces of information. I see the two pieces of information because what makes this point be what it is it's the intersection of this edge of the triangle and this edge of the triangle. In other words, this point right here is it's described by saying that I simultaneously lie on this vertical edge and I lie on the slanted edge. So now I have two equations and two unknowns, and I should be able to solve two equations and two unknowns and determine exactly what the x and y coordinates are. Obviously, this one already tells me that x is equal to 0, and then, just as obviously, if y is equal to x, then y is equal to 0 as well. So I've decided what I'm sure you guys already knew, which is that the y coordinate in that point is 0, and it's the smallest y coordinate that you're going to see anywhere in our set. But please get used to thinking about it this way. When you want to figure out the x and y coordinates of a point, you've got to write down two pieces of information that describe what makes that point be what it is. In the same way, I need to know the largest y coordinate that comes anywhere in my figure. And so I need to see that point first. I need to go as far to the north as I can, and that'll tell me, well, any of these points, they're all tied for having the largest y coordinate. So let's pick one of them and see if we can figure out what its y coordinate is. And again, I would describe this point by saying two things about it. It's on this line and it's on that line, which means it satisfies this equation and it satisfies that equation. So the two equations that describe this point are x equals 0 and y equals 1. And just as in the previous case, I have to take those two equations and solve them to figure out the x and y coordinates of the point. Well, there's nothing to solve. It already says x equals 0 and y equals 1. So clearly the maximum y coordinate that you see anywhere in your set is 1. Now, it's a little bit harder actually to get these limits of integration that go on the inside. I'm going to do the same kind of a thing. I'm going to ask you about the smallest and the greatest x coordinates. And of course, the way you get a small x coordinate is going west and a large x coordinate is going east. But the difference is, you have to remember that when you perform this inner integral, you'll be integrating with respect to x and treating everything that's not an x as a constant. In particular, that means that this y is being held constant. So as I'm doing this inner integral, I need to think about y as being constant. And if y is held constant, well, the set of points in the plane where the y coordinate is constant makes a horizontal line. Depending on what constant you've chosen it to be, that line will be higher or lower, but you've just got a horizontal line, and within this inner integral, you're just paying attention to the points that are on that horizontal line. So now it's not really the triangle that matters anymore, it's just this line segment. That's the portion of the triangle that lies on that horizontal line. So if I can have a little blow up of that, let's stare at this subset of the plane now, just that line segment, and ask for the minimum and maximum values of the x coordinate anywhere on that set. So again, to get my minimum x coordinate, I go to the left as far as I can, to the west, and to get my maximum x coordinate, I'll go as far as I can to the right. Well, I'll say the same thing I did in the previous one. I can see that leftmost the leftmost point, and if I want to know its two coordinates, I should write down the two pieces of information that I know about it. One is that it's on this line where y is a constant, and the other is it's on this vertical line where x is equal to 0. Two pieces of information will let me determine the two coordinates, although actually I know what they are. The x is 0 and the y is whatever the constant is. So the x coordinate at that leftmost point is 0. And finally, I have one more to figure out, and this is maybe less obvious. I need to get the coordinates of this point, and I would describe it as being the intersection of my chosen horizontal line and the other edge of my triangle whose equation was y equals x. So now I have two equations and two unknowns, and I can use those two equations to determine the x and y coordinates of this point right here. it says on this line that the y coordinate is c, and it says on this equation that the x and y coordinates are equal. So the x coordinate is also c. So I guess I'd like to put c up in this spot, except I don't know what c is. C is whatever the constant value is that you're holding your y coordinate to. Well, the c coordinate is equal to the y coordinate on this line, so it's the same as just saying that the x coordinate will be equal to whatever the y coordinate is. And this is the way your Fubini problems will tend to look when your domain of integration is something other than a rectangle. If it's not a rectangle lined up with the axes, you're going to have limits of integration that are constants for your outer variable. And on your inner limit of integration, these are not necessarily constants. They will be, well, they'll be constants when you hold that other variable constant. So in general, these limits of integration will be functions of that variable. Okay, let me pause here. Malik, you have a question? I see your
Yes.
hand up.
So I was just wondering, is there a reason why you integrate with respect to dx first as opposed to doing dy?
In this particular case, it was because I knew it would get me to the answer a little faster, but I just know that from experience. You guys don't know that. I will show you that you can do it in the other order, though. We'll do this one first, and then we'll come back to the other one.
And I was also wondering, can you integrate like the constants first and then do the variables on the outside, or does that would that matter or no?
It would definitely be wrong if you had variables in these spots and constants in those spots. Among other things, let me point out that we're looking for the volume of a very particular figure. We're looking for a number. And if you went through all the process of integrating and you had y equals something involving x here or here, and you're using, you'll use the fundamental theorem of calculus and you'll plug in these two values for y, well, then you'd end up with x's left over. So that's definitely wrong, and I got to tell you, people always mess it up. It's something that when I look at people's exams from this part of the course, there's always somebody that gets things in the wrong order, and they're putting non-constant values in those two spots. So you know that it's wrong because at the end of the day, you're looking for a number. So good question. I'm glad you asked. And I know somebody's going to make the mistake anyway, but let's just cross our fingers and try to minimize it. All right. So I just spent kind of a long time just making sure that I could write the original integration problem as a double integral. Having done that, now I can evaluate this double integral. So let me rewrite it for you. So I have it on a fresh sheet of paper. So I'm trying to compute the integral as y goes from 0 to 1, and as x goes from 0 to y, and my integrand is 1 minus y squared, integrating first with respect to x, and then with respect to y. Now, notice when I set up the limits, set up the integrals here, I started with the outside integrals and then worked my way inward. Now to evaluate the integrals, I'm going to start on the inside and work my way outwards. So don't say first variable and second variable. Talk about inside variables and outside variables. So I won't change this outside stuff. But on the inside, I look at this function of x and y, and I will now find an antiderivative with respect to x. I'm going to use the fundamental theorem of calculus here. My antiderivative with respect to x is, oh, yay, this is all constant. And the integral of a constant, the antiderivative of a constant is just that constant times x. And now when I evaluate that function of x at these two values of x and subtract, what I'm going to find will be x times y times 1 minus y squared minus 0. The other one will give me a 0. And that's what I have to integrate with respect to y. This integral now is pretty easy. If I wanted, I guess I would do a u substitution, let u be 1 minus y squared, so du is minus 2y dy. And well, y dy is part of my integrand, and the rest of this is just the square root of u. So let's see, when y is equal to 0, u is equal to 1. When y is equal to 1, u is equal to 0. My integrand, this part of the integrand is u, square root of u, and the rest of it, y dy, it's half of the du, oops, well, minus a half of du. So I hope you don't mind me speeding through the Calc 1 tools. I can get rid of this minus sign by switching the order of my limits of integration. I can pull this 1/2 out. The square root of u, I would write it as u to the 1/2. And now I can find an antiderivative of this, u to the 3/2 times 2/3. I don't want to forget the 1/2 in the front. And I stick in the two endpoints, 0 and 1. And I have just enough space to write in that answer is a 1/3. So that should be half of the volume of the figure they wanted in the original figure. So I believe that the volume of the intersection of those two cylinders should be 2/3. Is there any chance that actually was one of the answers that was on the answer key? Does anybody have the homework set available?
Yeah, mine was from like, mine radius was 3, so it was twice of that number, so it was correct. Yeah.
If your radius was 3, everything should scale up by a factor of 9.
Yeah, so it's correct.
Okay. Yep, there you go. Okay. It's always reassuring when I get the same answer that I did when we wrote up the answer keys. All right, let me address a point that was raised earlier. Could we have done this by somewhere in the middle? I made the arbitrary decision to put X on the inside and Y on the outside. So you should say, well, could you do it the other way? And the answer is yes. If you want to integrate over this region in the XY plane, it's the same region and the same function. But if you want to use Fubini's theorem in the opposite order, you're welcome to do so. Put X on the outside and Y on the inside. Oops. The function hasn't changed, but the letters X and Y are swapped around everywhere. So now what's the procedure that you go through? Oops, sorry, I keep writing 0 for some reason. Now I should be scanning, I first scan my whole figure looking for the least and the greatest values of the X coordinate. Low X coordinate is that way, high X coordinate is that way. And well, I'll spare you the laborious calculation, but you know that a point down here has an X coordinate of 0, and a point over here has an X coordinate of 1. So those are the smallest and the greatest values of the X coordinate anywhere in my set. As I move to the inner integral, everything that I do with this integral will hold X constant. And if you hold X constant inside this set, here's all the points where X is held constant. If I now want to set this up as to get the limits of integration, I need to stare at or ask for the least and the greatest values of the Y coordinate, not on the whole triangle, but just on the portion of the triangle that has this constant value of X. So I'm just staring at this line segment and asking for the least and the greatest values of the Y coordinate anywhere in here. The greatest Y coordinate would be obtained at the north end, and that's a 1. And the lowest Y coordinate is obtained at the south end. And that means I need to know the Y coordinate of this point. Well, the two things that I know about this point is that it lies on this line, where Y is equal to X, and on this line, where X is being held constant. So if you put these two equations together, they tell you what the X and Y coordinates of that point are. X is whatever the constant is, and, well, Y is supposed to be the same. So you could have this vertical line at X equals 0, or X equals 1/2, or 2/3, or 1, whatever point you've chosen, the X and Y coordinates of this point would be that number, and that would be the number that you would put into this spot. But in general, since I don't know which vertical line I'm talking about, as I move to the inner integral, I'm just going to have to say that, well, the Y coordinate will be whatever the X coordinate is. So now I've written my integration problem as a double integral, but with Y on the inside. Absolutely fine. You're perfectly welcome to do this. What you notice as you do it, however, is that this one's a lot harder to work out. I would leave the outer integration symbols all unchanged, but in order to evaluate this inner integral, I have to find an antiderivative with respect to Y. Anybody got one handy? Yeah, no, I didn't think so. Does anybody remember how you would find an antiderivative of such a function? What technique did we use in calculus?
Trig substitution.
Yeah, trig substitution. So now you're going to have to say things like let y be equal to, I don't know, the cosine of theta, cosine of u or something, so that dy would be equal to minus the sine of theta, d theta. And so the dy here, I've got something that substitutes for that one. And if when I replace y being cosine of theta, you'll have 1 minus cosine squared of theta. So this is the sine squared of theta. The square root will just be sine of theta. And so my integral turns out to be the integral of sine of theta times negative sine of theta. And you'll have to know the values of theta that correspond to that value of y and this value of y. I know that y is equal, the cosine of theta is equal to 1 when theta is equal to 0. But now my limit of integration down here is a total pain in the neck. Let's see, I need theta to be the inverse cosine of y, and the y coordinate in question is equal to the x coordinate. So down here, I need the arc cosine of x. So you have to first anti-differentiate sine squared of theta with respect to theta, and then plug in that value of theta, which isn't so bad, and this value of theta, which is going to look terrible. Nonetheless, what you'll have will be some function of x that goes into this spot, and you can compute the integral of that with respect to x. Do I have any takers? Anybody want to do it that way? Yeah, no, I didn't think so. So this is actually a very important lesson to learn from Fubini's theorem. Yes, you can transform this surface integral into an iteration of two one-dimensional integrals, and yes, you are allowed to do it in either order, but there's no guarantee. I mean, and you're going to get the same answer because both of them will evaluate to whatever this volume, half volume, was. So they're both correct, but that doesn't mean that they're both equally easy. This would be a pain to keep going on this problem, although at least you could do it. Let me show you another example where you'd have more trouble. Well, actually, before I stop and do my next example, does anybody want to ask me anything about this example? So I spent a full half an hour or more on just this one problem, but it was useful, I think. Enrique, you got your hand up.
So with this, is it just something that we had to build intuition over time to be able to recognize which way will be more effective? Or is there some type of method or theory behind this?
No, it's just a matter of experience and taste, you know, which way you would prefer to do it. I will tell you this, if you're doing a two-variable integration problem, you only have two choices. You either put x on the inside and y on the outside, or the other way around. So spend a couple of minutes setting one of them up and see how it goes. And then if it doesn't look like it's going well, abandon that and go for the other one and spend at least a couple of minutes the other way. Of course, you might decide that the second way that you try is actually worse than the first one, so you might have to go back. But generally, it's, you know, if there's only two options, then you don't have to invest too much time in any one of them to decide which one of the two routes is going to be better. I will caution you, one of the things we want to talk about is integrals over three-dimensional regions. Everything that we've been saying about how integration works, the general theory of integration that makes things like volumes or other calculations turn into integrals, that stuff is all still the same. You're going to take a three-dimensional region and chop it up into little bits, and you multiply the size of each one of those bits by the value of some function. Of course, when I say size of a little portion of three-dimensional space, that means the volume of a portion of three-dimensional space. And you'll have to be evaluating a function of three variables at a point inside each one of those little pieces. But conceptually, except for the fact that we're changing areas to volumes, the general theory of integration works just as well when you integrate a function of three variables over a subset of three-dimensional space. And then Fubini's theorem works equally well for functions of three variables too, but what Fubini is going to give you is a way to write that kind of weird integral as now a succession of three integrals, three one-dimensional integrals like you had in Calc 1. And the reason that I mention that at this moment is because If you have 3 variables, x, y, and z, there are actually 6 different orders in which you could put the integrals into the problem. You could integrate with respect to x on the inside, then y, then z on the outside, or y on the inside, z in the middle, x on the outside, or whatever. It's 3 factorial. It's 6 different ways to arrange the variables. So if you had to do a triple integral like that, that could take longer to decide which of the 6 is actually going to be the best. I won't give you any problems where you have to really go through all 6 of them to find one that's going to work. If I give you a triple integral, I will guarantee you that either it'll be obvious somehow, or it won't make a difference somehow which way you order them, or maybe they'll all work equally well or something like that. But yeah, in principle, it's a matter of some experience to know which order of integration to try. Let me show you a few other examples, and I know I have not too many minutes left. So here's another example. Suppose that I wanted you to integrate over, let's use the very same region that we had before. And suppose that the function that I wanted you to integrate was this function, sine of x squared. So that's a function of 2 variables. It's the sine of x squared plus 0y. There. So Fubini says you're welcome to write this as a double integral in either order. In both cases, you'll keep the integrand unchanged. But you can either have x on the inside or y on the inside, and then, of course, the other variable has to be on the outside. And in each case, you'll have to write in what are the limits of integration. It'll be constants for the outer variable. Let's see, the x's go from 0 to 1, and the y's also go from 0 to 1. In this integral, let's see, if I hold my y's constant, then my x-coordinates go from 0 up to, the x-coordinate can be as big as the y-coordinate. And in the other, if I do it the other way, if I hold the x constant, then my y-coordinates can go as high as 1, but the lowest y-coordinate is the same as the x-coordinate. All right, so I just set up the 2 double integrals for you to choose from. Of course, I got exactly the same limits of integration as we had in the previous problem because I've got exactly the same region. I've done all of my work so far looking only at the region of integration and not at the function that I'm going to integrate. So now it's time to do the integrals. Which of these 2 integrals surrounded by square brackets would you rather do? You know, an
both look pretty hard.
But they're not.
They're not.
Because look, this would ask you for a function of x. I mean, in both cases, your instinct is you're just going to use the fundamental theorem of calculus. That's fine. For an integral of a function of 1 variable, go ahead and use the fundamental theorem. That means you have to find the antiderivative and stick in the endpoints. But you don't know an antiderivative of the sine of x squared, not with respect to x. On the other hand, if you think of this as a function of y, well, as a function of y goes, this is constant. There's no y's in there. So as a function of y, this is a constant, and the antiderivative of a function of y, a constant function, is just that constant times y. And so I'm just going to get sine of x squared, which is a constant, times y, and I evaluate it at these 2 endpoints, y equals x and y equals 1. And now I'm off to the races here. I've got some way to actually evaluate this inner integral, the second one, not the first one, but this one works out all right. My function of x that I'm going to have to integrate will be, I evaluate this function of y when y is equal to 1. Oh, actually, this isn't as easy as I thought. Minus the same function of y evaluated at this value of y, so that'll be x times the sine of x squared. There. So I got further. I now have just a single 1 variable integration problem to do. And unfortunately, I chose a triangle where this turns out to be kind of hard, so this doesn't seem to be working too well, sorry. But it's better than what I had the first way when I got stuck I was dead in the water on the very inner integral. I couldn't do a thing with this one.
Dr. Resson?
Yeah, go ahead.
So I'm kind of confused on like the bounds for the second integral. So like, why couldn't you do 0 to x, like for the inner?
You wanted this one to be a 0 and this one to be an x?
Yeah.
All right, don't do that. I mean, I know why you want to do that because it looked like it worked in that case. But don't. You have to remember the way I was trying to describe it. What you want for these two limits of integration are the least and the greatest values of that coordinate anywhere in the part of our set that has the outer coordinate held constant. When you hold x constant, you're stuck on this vertical line segment. And you're supposed to stare just at the points on that vertical line segment and tell me about the least and the greatest values of the y coordinate. So go all the way to the south and all the way to the north and tell me about the y coordinates of those 2 points. You don't see any points in here that have a y coordinate of 0. That point would have to be down there. Since I don't have any points in my original region that have a y coordinate of 0, I definitely cannot have y starting at 0. Y has to start with the value of x. Let me say it another way. If I presented you with this problem, suppose I asked you to integrate some function over with limits of integration like this. I think this is what you proposed. Y would go from 0 to x. If I asked you to use Fubini's theorem and write this as a double integral in the opposite order, I could do that, but in order for you to resolve that problem, you'd have to first pass through Fubini's theorem to write this as a double integral over some region of the xy plane. So let's try to reconstruct what that region would be. It's going to be a region that has x coordinates going as low as x equals 0 and as high as x equals 1. So there are points in my figure that should be on those 2 vertical lines, but nothing outside of those 2 vertical lines. And on any intermediate vertical line where you hold x to be some constant between 0 and 1, let me show you what points you're going to get by looking at the possible y coordinates. On any other intermediate vertical line, you want points that have y coordinates as low as y equals 0, which is on this line. And you also want points that have a y coordinate that's as high as the current x coordinate. So you want the bottom will always be on the horizontal axis, but where the top is depends on what x coordinate you've currently got. When your x coordinate is small, like this vertical line, your y coordinates are going to be trapped at a low value. And when your x coordinate is held at some high value, well, then the y coordinates can get higher too. And in fact, when you look at all of those top points, they all have a y coordinate that's equal to their x coordinate. In other words, they all lie on the line y equals x. So when you see these limits of integration, these 4 expressions put together, they are describing for you this triangle that goes between the line y equals 0, the line x equals 1, and the line y equals x. To my way of thinking, there's no way to do this except to actually stare at these 4 expressions and piece together a picture of the region in the plane that would give me these limits of integration. And then after you've got it drawn this way, now you can start to go through the kind of process that I did to go from the picture to get the 4 limits of integration. I did it here and I did it here from this picture. So you can do it now. You can take this picture and rewrite this as being a double integral the other way, where y goes from, I guess, 0 to 1, and the x coordinates, let's see, when you hold y constant, x will go from y up to 1. So I don't remember if I put any into the homework set, but have a look at the problems in the book, and you will see that this is a classic kind of thing for an instructor to do, is to give you a double integral written out with the variables in one order and ask you to flip them. And there's really no way to do that except to go by way of the picture. Yeah, everybody's quiet. Okay, listen, I went over. Sorry about that. I'm trying to hold myself to just an hour. I got my office hours. I'll be back in my office. I'll be Zooming again at 1 o'clock and then at 3 o'clock. So if you have questions, stop by and take advantage of Piazza. But let me just emphasize what I said at the beginning of the hour. For right now, the only problems on the homework that I expect you to be able to do are the first 6, and the others will be on material that we'll get to next week. Okay? So have a good weekend, and I'll see you guys again on Monday.
Okay, thank
Dr.
you.
Russo?
All right. Were you asking a question, somebody? I heard it.
No, I was just saying thank you.
Okay, yep. All right, we'll see you on Monday.